Hey everyone, today we're going to be learning about formal charges. So, a formal charge basically assigns a charge to an atom within a molecule. And it's important to know that when you're calculating this, you're assuming that in each bond, the electrons are being shared equally between the two atoms that form that bond. So, an application for formal charges comes when we talk about resonance structures. Now, resonance structures they basically occur when the atoms in a molecule remain in the same place, but the electron placements change. So that means the bonds between atoms change and the number of non-binding electrons or lone pairs on the atoms can change as well. And we use formal charges to figure out which of those resonance structures are like the largest contributor to the actual molecule, because the formal charges on the most stable resonance structure will be closest to zero. Now, to calculate formal charge, we're going to take the number of valence electrons and subtract it by the number of non-binding electrons, or lone pairs, those will be dots on our Lewis structure, minus 1/2 times the number of electrons in bonds, binding electrons, and those will be the bonds between the atoms that you see. And an easier way to calculate this is to take the number of valence electrons and just subtract it by the number of lines and dots surrounding that atom in the molecule. So we're going to go through some examples. The first is this NH4 plus ion. And we're going to start by calculating the formal charge for the nitrogen. Now the nitrogen has 5 valence electrons. It has no non-binding electrons. I don't see any lone pairs around the nitrogen, so we're going to put a 0. And then for binding electrons, or electrons in pairs, I see 4 bonds around the nitrogen, and each bond is going to have 2 electrons. So if you had a double bond, that would count as 4 electrons, and a triple bond would count as 6. But this has 4 single bonds, so we're going to put 1/2 times 8, and that equals 5 minus 4, which equals a formal charge of +1. And whenever you calculate a formal charge, you want to make sure you put it around the atom with a little circle. Now, if you were to calculate it the easier way, with just the number with the valence electrons minus the number of lines and dots around the atom, we would quickly see that we have 5 valence electrons and we have 0 dots, but we have 4 lines around the nitrogen. So we also do 5 minus 4, and that equals 1. Now for the hydrogens, each hydrogen here is going to have the same formal charge, and you can check that for yourself as well. But let's say we're talking about the hydrogen on the right, this hydrogen. Hydrogen itself has 1 valence electron. There are no lone pairs or non-binding electrons, and there are 2 binding electrons because it has 1 single bond. So 1 minus 0 minus 1/2 times 2 equals 1 minus 1 equals 0. And if we were to do it the second way, the number of valence electrons is 1, minus the number of lines and dots around the atom is also 1, so we get 0. Now, one thing to note with formal charges is another way you can check is to make sure that the sum of all your formal charges equals the charge of the entire molecule. So here, the only atom with a formal charge was nitrogen, which had a +1 formal charge. All the hydrogens had a formal charge of 0, and that makes sense with the overall charge of the atom, which was just +1. Now we can do the same with H2S over here. So starting with the sulfur, sulfur has 6 valence electrons, and it has 4 non-binding electrons. It has 2 lone pairs, and each lone pair has 2 electrons, so there are 4 non-binding electrons. And sulfur has 2 bonds, and each bond is with 2 electrons, so that's going to be another 4 binding electrons. So this is 6 minus 4 minus 2, which is 0. And if we were to do it the easier way, 6 valence electrons minus, there are 6 lines and dots around the sulfur. So we're going to have 6 minus 6, which also gets us 0. And this is the same case for the hydrogens in the last molecule. Each hydrogen has 1 valence electron, 0 non-binding electrons and 2 binding electrons. And if we were to do 1 valence electron minus 1 line and dot, or line or dot around the atom, we also get 0. Once again, the sum of the formal charges, there is no charge on this atom, and each of the atoms have a formal charge of 0. So that checks out as well. Now, I wanted to also go over an example that includes resonance. So these two structures are resonance structures for CO2 or carbon dioxide. And the way you often denote resonance structures is with that double-sided arrow in the middle. So first, I want to start with the first oxygen, or the oxygen on the left, for this molecule on the left here. And we're just going to go ahead and do it the quick way. So oxygen has 6 valence electrons. And in total, it has 6 lines and dots around the atom. So 6 minus 6 equals 0. Perfect. So oxygen has a formal charge of 0. And then we can also see that it's the exact same on the right side. You can go ahead and check it for yourself with this oxygen right here. And you're welcome to test it out yourself and check that it's also 0. For the carbon, carbon has 4 valence electrons, and it has 4 lines around it. So we can go ahead and find that that carbon has a formal charge of 0 as well. So all 3 molecules in the resonance structure on the left side have a formal charge of 0. So this is looking pretty good for being like the largest contributor to carbon dioxide. Now for the molecule on the right, we'll start with the oxygen on the left. And oxygen has 6 valence electrons, and it has 5 lines and dots around it. So it has a formal charge of positive 1. So we're going to go ahead and put a plus on it. Now the carbon has 4 valence electrons, so we're going to put the 4 there, and then it has 4 lines around it, no dots, so we're going to subtract 4, and that has a formal charge of 0. And for the oxygen on the right, it has 6 valence electrons minus, now it has 7 lines and dots around it. 6 dots, 1 line, for a total of 7. So that has a formal charge of negative 1. So we're going to put a minus on it. And if we had a plus on one oxygen, we would have had to add a negative on another atom just to make sure that the sum of the formal charges added up to 0, which was the charge of the overall molecule. So based on this, we can predict that the resonance structure on the left is going to be a larger contributor to the molecule of CO2, or it's more accurate in depicting how it's found in nature because the formal charges are minimized. Thank you so much for listening.